Good morning, everyone. Hope everybody's doing well this morning. It's kind of a dreary, drizzly day in my part of the world. I'm not sure. I think this is going out to people all over the planet, which is kind of an amazing thing if you think about it in the sort of context of human history. But yeah, in Ontario, in Hamilton, Ontario right now, it is just this really gray day. It seems like November has come quite early this year. But anyway, how are y'all doing? I hope you're doing well. We're gonna try to get things... Oh, that's the other class. Jeez. You don't have to worry about that. That's the other class. But here we go. We're gonna see if we can finish off this slide set today. So, let's get to her. You know, it would be good if we maintained only being a week behind. Anyway, so if you recall, last time we were talking about this well-familiar and well-hated example of trying to find the x-intersect of a monotonically increasing function. So, we're going to do a Python version of this. The interesting thing about Python is that you can pass functions as arguments to functions. This is actually not something unique to Python. You can even do this with C. As it turns out, you can do it with function pointers, but that's neither here nor there. So let's take a look at the encoding of this algorithm. Get it, shall we say, intersect.py, and then we shall python3 intersect.py. Python3 intersect.py. There we go. We'll have that ready. So, if we just take this, scoop it out, plop it in there, fix the tabbing. So the question is, what's going on here? There we go. So, x-intersect is being given f, which is the function that is monotonically increasing. We are being given the upper bound, or the lower bound and the upper bound, a and b, and we are being given some epsilon. We're going to loop over this. This is going to be a looping algorithm, the exit condition of which is that b minus a is less than epsilon. As soon as b minus a is less than epsilon, this loop will terminate, and we will return both the upper and the lower bound. If you wanted to have one return value, you could return the average of these two. It doesn't really matter. So, for each iteration of the loop, we calculate m, the midpoint, as being the average, the value that's in between a and b. It's a plus b divided by 2. If f at m is less than or equal to 0, then we set a equal to m. Otherwise, we set b equal to m. And then we go back to the beginning of the loop and continue to execute it. So, in effect, this interval that's represented by a and b will be reduced by half each time, and in the same mechanism as the binary search algorithm. And eventually, it'll become so narrow that the width of the interval will be smaller than whatever you have specified as epsilon, so long as epsilon has been specified as something greater than 0. When that happens, we consider ourselves to have found the x-intercept within a reasonable margin of its actual value, and then we return what that is, what the interval is. Questions? Will we ever go over how to turn our .pies into .exes? Shouldn't I be using the absolute value? Yes, I should, actually. That is a very good point. So the point that your esteemed colleague brings up is that, well, actually, in this particular case, you don't have to take the absolute value. Ordinarily, it's a good idea to take the absolute value when you're creating a loop condition such as this, because if a ends up being greater than b somehow, if this is negative, then that's always going to be less than, or, like, you're no longer testing for the magnitude of the thing being inside of that epsilon. Negative numbers can mess that up quite substantially. That's why it's usual to take the absolute value. Of course, because of the way that this algorithm has been designed, b cannot ever reach a value that's less than a. So, in that sense, it's you don't actually have to worry about the absolute value being applied in this particular case. However, it is a good idea, generally speaking, when you are applying this type of test. So that's a good point. Shouldn't we check if A and B have a different sign? That would be another thing that you could do for sure. So checking to see if A and B have different signs, that's sort of, we don't necessarily have to check that because of the assumptions that we've made going into this algorithm. Remember, we've made some key assumptions here. The first assumption that we made is that epsilon is greater than 0. The second assumption that we've made is that f is monotonically increasing on A to B. And another assumption we've made is that f at A is less than 0 and f at B is greater than 0. So because we've assumed f is monotonically increasing, and if we go back in the slides, you'll see that these assumptions come up. Because A is assumed to be, basically we are assuming that the intersection is occurring somewhere between A and B. And because it's monotonically increasing, this means we can derive from that result the fact that f has to be less than 0 and b has to be greater than 0. Unless f or b are, in fact, the intersect itself, which is a thing that's easily tested for. So if f at m is equal to 0, you could return m comma m, because we found it exactly, something like that. If f at m is less than 0, do that, and in the other case, there you go. So that's a slight modification of the algorithm which takes into account the fact that you might actually hit the x-intersect exactly when you calculate m. This is a reasonably uncommon occurrence given that we're working with floating point numbers, but there you go. Good questions, good questions. Is the midterm... Oh, yes. Is the midterm covering topics up to the end of the week 7 slides? No. No, it's covering up to the end of functions and recursion, which is topic 5. We're not covering... The midterm coverage does not include numerical computations because I think it's really a nasty thing to do to people to not give them any time to actually study the material that they're being presented in class. So, no, this set of lecture slides is not going to be on the test. There you go. Okay, so, at least I don't think so. So, if we define a couple of functions, say define function 1 of x is return x times x minus 4, and if we define function 2 of x is x times x minus 2, you could use a little bit of algebra to a little bit of mental algebra to understand that the x-intersect for this guy is going to be 2, and the x-intersect for this one is going to be root 2. But, you know, we're going to see how close we can get, how close an approximation to that we can get. So, if we invoke, let's print the invocation of this function on f1. We shall assume that the x-intersect is occurring somewhere in the interval from 0 to 100, and our epsilon is going to be 1 times 10 to the negative 8. This is programming language shorthand for scientific notation. If you just put an e here, that is known to mean times 10 to the e. So, that's cool. In there. So let's see how this works. Incidentally, I don't think that making executables ever really comes up in the lecture slides. I will leave that to you guys to investigate on your own, should you be interested. So, there we go. Our first interval, we know mathematically from our knowledge of algebra that we were looking for the value of 2. And you can see we've got 1.999 and 2.0000 with some junk on the end. But that is a reasonably tight interval around 2, which is what we would expect. Similarly speaking, we've got a very tight interval around root 2 that is accurate to 7 decimal places. And 7 decimal places is probably usually enough for most people. So, that's cool. So the algorithm works. Let's try tightening the bound a little bit. Let's see what happens when we ask for a precision of 15 and 16 decimal places. Oop. And just for fun, we can also use an anonymous function instead of predefining our f functions. So, there we go. You can see we get 1.9999998. There we go. And you can see that after that, we're starting to run into those floating point errors or floating point adjustments that are very usual. In fact, if you want to take a look at the the actual things going on back there, you can format x.60f, and I think this is it. I hope I haven't switched these. Yeah, so there we go. That's Yeah, so that's 2 exactly, which is interesting. So there you go. The only reason that we got 2 exactly when we did this is because the answer to this problem is rational. It might be interesting to see what happens when we do f2, which is an irrational root. Oh, look. Is the program hanging? I think the program is hanging. So, yeah. If you're asking, you remember that situation we were talking about earlier, where if you ask for epsilon being 0, it'll run into an infinite loop. This is that situation, except we haven't asked for epsilon being 0, we've asked for epsilon being so small that the values that A and B have are like oscillating between some very, very small value and never actually hitting the actual answer, which is an irrational number. So there you go. Questions? What if the function wasn't monotonically increasing? Then we would use a different algorithm. Are we expected to try except for domain errors? Once we learn try except, then yeah, that would be a thing that we would. That's like a very good test question. Do you understand how to raise an exception? Is, here are some assumptions about the input to this function. Please raise, whatever error based on whether or not the inputs are actually inside of the expected domain. Doop, 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 doop. Cool. Right. Okay. Good. So let's move to a different one. Let's talk now about approximate square root. We'll get rid of this stuff, because who the heck needs it? So, it turns out that square roots are actually a reasonably difficult thing to calculate. If you've ever seen the manner in which a square root is actually calculated in terms of the algebra that has to go into it, and you have to do like a binomial expansion, and it's all very complicated. I forget how it goes exactly, but it actually, unless you've memorized the square root, it takes quite a lot to calculate one. That's why, that's why you have, it's basically on a memorization basis rather than normally being actually calculated. But so let's create an algorithm that calculates for us the approximate square root of some number n. So we will define the approximate square root such that if a squared is less than or equal to n, and n is less than a plus 1 squared, then we'll have found, then a will be the approximate square root. So it's kind of like the Price is Right thing of close to but not going over. So one way to compute the square root is by linear search or exhaustive search. So in the linear square root algorithm, what we are doing is we are starting at 0 while a plus 1 times a plus 1 is less than or equal to n, a plus equals 1. Return a. So we are going through each value of a, incrementing that until we hit this condition where the next one would put us over the value that we're looking for. Then we stop and return a. This is fine. This works. the linear square root of 25, for example, will be 5. The linear square root of 27 will be 5 as well. The linear square root of 35 will also be 5, but as soon as you go above 36, which is 6 squared, it goes to 6. So that's your approximate square root. And, you know, if you wanted more accuracy, you could certainly imagine an algorithm that searches through, you know, all of the tenths, and then the hundredths, and the thousandths, each of those smaller and smaller place values in order to come up with a better and better approximation of the square root. So, when we ran it for 27, this is a trace of what the program was doing. A was initially 0. Once we hit, it would then be incremented by 1 to 1, 2, 3, 4, and 5 sequentially, and then it would stop at 5 because 5 plus 1 times 5 plus 1 is 36. 36 is not less than or equal to n. Therefore, the while loop stops and we return A. So, question, for n is greater than or equal to 0, how often is B executed? And again, I'm going to skip these because it takes too long and we need to keep moving, but the answer is the square root of n, because, of course, we do one iteration for each, each number. The number of iterations is equal to whatever the output is, because it's going up by 1 from 0. So, B is executed exactly as many times as whatever the output of the function is, yes. Hence, A is executed root n times. So, it turns out that we could actually use a similar interval search type operation in order to make this algorithm more efficient. Since the thing we're looking for is intrinsically ordered, we can use another one of these interval narrowing algorithms. So, let's take a look at it. So we're going to suppose that we have an A and a B such that the root is between A and B. So A is greater than or equal to B, or A is greater than or equal to 0, and B is always greater than A. And when we finish, we want A squared to be less than or equal to n, and B squared to be greater than n. So, let's do this. So, interval square root. If we take an A and we take a B as well, while A plus 1 is not equal to B, C is equal to A plus B divided by 2. There we go. If C times C is less than or equal to n, then we set A is equal to C. Otherwise, B is equal to C. Then we return A. We can even put some print functions in this to make it a little more clear as to what's going on. Type error. Missing 2 required positional arguments. Oh, right. So let's imagine we know it'll be somewhere between 0 and 8. So we start at 0 and 8. We then go to 4 and 8. We then go to 6 and 8. And then it returns 6. So there you go. Questions? Yeah. So, good. So there is also, you don't necessarily have to, so in this version of the algorithm, we're giving up front what B is, but it's also possible to calculate what B should be, like what a good starting B would be. If you sort of start off with B being equal to 1, you can simply while loop over the idea of B being less than or equal to n, and each time that's the case, you multiply B by 2. This will get you to an approximate upper bound reasonably quickly. So, yes. Gonna just go through that. So, the first loop sets B equal to 2 to the k, which is greater than the square root of n after k executions. The second loop halves the interval b minus a at every execution until a plus 1 is equal to b. Hence, it also takes k executions. So, each loop takes k log base 2 of b. So we would say that the runtime of this algorithm is log base 2 of the root of n, which is pretty good. Considering our linear square root algorithm took the square root of n number of executions, this one takes log base 2 of the square root of n executions, which is really good. So, now for something completely different. Let's talk about Pythagorean triples. So, for those of you who, everybody should know Pythagorean theorem. A Pythagorean triple is it's three whole numbered values, or integer values, such that when they are the sides of a Pythagorean, or when they are the side of a triangle, that triangle is a perfect right-angle triangle. So, here is an algorithm which calculates Pythagorean triples. Just gonna copy that, and then when it finds them, it just prints them. There we go. Print Pythagorean triples. And we shall do this up to n. Or no, sorry. We'll do this up to 100. So here are all of the Pythagorean triples that exist between for side lengths that go up to 100. There we go. But you'll notice that we have some repeated items in here, which, is fine, but maybe we can come up with a better solution to that. Incidentally, C is being defined as always being the hypotenuse in this particular example. So, for n is greater than or equal to 0, how often is A executed? Well, we've got 3 nested loops here. So, it would be n cubed. Because whenever you have a loop, you multiply the number of times that loop executes. So when you have nested loops, each loop nesting is 1 power of the number of times the loop executes. So there you go. N cubed. So we can immediately, by making a simple observation, we can immediately exclude a large number. We can actually eliminate one of these loops entirely, because this algorithm, as it's currently written out, checks each value of c in the range in order to see if a squared plus b squared is equal to c squared. But we know that there is a well-founded mathematical relation that we can rely upon that tells us what c has to be for a particular a and b, assuming that the triangle is right-angled. So we can use that. We can calculate, and we could even use our binary square root algorithm to do so. We can calculate what c has to be, and we can then check to see if c is a whole number or if it's a fraction, if it has a decimal component. Because if it's not a whole number, then it's not a Pythagorean triple. Another way of doing this would be as follows. Remove that. If a squared plus b squared to the power of 0.5, if that is that modulo 1 equals 0, then we can print it. So we're calculating c, which is the square root. C is a squared plus b squared, and then you take the square root, and then we are calculating what the decimal remainder is, if there is any, by taking the modulus of 1. So let's see if that works. Oh, c is not defined. Yes, that's true. Let's move that there. So we'll notice that we get basically the same values that we got before. The only difference, of course, is that this last number is a float now. And, if we wanted to, we could convert this to an integer, and everything would be hunky-dory. There you go. In fact, we're even getting we're getting a larger range of Pythagorean triples than we did before, because we are inclusive of c's that are greater than 100, which we weren't before. We were stopping at 100. There you go. So, in this new version of the algorithm, how many times is this inner part being executed? And the answer to that is, of course, n squared, because we are only having 2 nested loops now instead of 3. So, if you consider the rate of increase of n cubed versus n squared increases a lot less quickly, which means it's more desirable in terms of runtime. Never seen a nested for loop before. Yes, you can have a hypothetically infinite number of nestings of your loop structures. Yes. So, we can make one further observation, which is that 3, 4, 5 and 4, 3, 5 are both printed, but is it necessary to print both of these? And you can see that that's like, for example, 2172 is there, and 7221. All of these values are being doubled. Hypothetically, if we're only interested in printing the unique Pythagorean triples, then we can easily modify this in order to accomplish that. Rather than starting from 1 each time with the range of b, we can start from a each time. This will result, this will effectively exclude half of those. So if you'll notice, first of all, the list is a lot shorter, and second of all, you'll notice that we've got 3, 4, 5 and not 4, 3, 5 or any of those other ones. Because b must be greater than a, because that's the constraint that we've added by making b start at a, you don't get this case where you have the version where a is less than b and the version where a is greater than b, because a is always going to be less than b now. So there you go. Cool, cool. Yeah, so we're going to get into this a little bit when we in the next few slides, but yes, when you are considering runtime, there are two things that are primary contributors to runtime. Number one, loops are primary contributors. So, let's see. Can I explain this quickly? So, your runtime could be expressed as, I'm just going to use this as my chalkboard here. Your runtime could be expressed as a algebraic equation, right? So it would be something like a times n squared plus b times n plus c. So where n is the input. So anything that's in C is stuff. That's the amount of runtime that has to occur no matter what your input is. So in the case of our previous example, if we had, like, you know, some operation here, like we were printing something, this would be executed no matter how big the interval. Like, even if the loop was never executed at all, this runtime would still be contributed, so that would be in C, right? B is the number, like, if it's the amount of time that it takes to execute everything inside of the first loop. So if you had another, you know, something that took time here, this would be executed n times. So the amount of time it takes to execute this would be multiplied by n, and then that would be contributing to the runtime in that manner. And in the same way, A, in this case, would be everything in here, right? So if you have things in here that are dependent on n, this, you know, you could have like a multiplicative factor of log base 10 of n, or something in there. You know, it would be log base 10 of n, a plus whatever log base 10 of n. So that's all. So that's sort of how the characteristic equation of the runtime sort of develops. However, we're going to get into this very shortly. There's a way of approximating this that's known as big O notation, which is something that you guys are going to get into when you take your algorithms course next semester. I think you guys are taking an algorithms course next semester. But essentially, what we're concerned about is which one of these terms most characterizes the runtime as n increases. So you can sort of think of it as the limit as n approaches infinity. So as n increases, the actual magnitude of r is going to be contributed primarily by this term. The constant term obviously is not going to contribute very much at all unless it's very, 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 very large. So we sort of abbreviate it away. Same thing with the b times n term. This is the linear term. The linear term is obviously increasing as n increases, but the rate of its increase is very small in comparison to n squared. Over time, n squared is going to overwhelmingly dominate the contribution to the runtime. So we abbreviate that away as well. In essence, the runtime of the algorithm is contributed to primarily by whatever the largest term is. So in this case, it would be n squared. However, and there's one more approximation that we make, and that is this a factor is it's a really hard thing to actually pin down. Not only does it vary with the actual code that's contained inside of the loop, it is affected greatly by things like the particulars of your operating system, the particulars of your hardware, how old your hardware is, all kinds of these very subjective factors. So in order to sort of try to take this and turn it into something that is a more objective sort of abbreviation of what the runtime is, we typically don't consider the constant factor. So we would say that the algorithm is big O of n squared. Big O notation is, generally speaking, a mechanism that algorithms people and researchers and developers use to try to classify algorithms. Classify algorithms according to the rate at which their runtime increases as you increase their inputs, which it turns out is actually one of the most important factors about an algorithm. So this is something I'm jumping ahead of the slides, but that's roughly speaking how you arrive at big O notation. So yes, I didn't predict the slides very much. So if we know how many steps a program takes depending on the input, we can use this to predict the execution time. This can be done without knowing the details of the processor and compilation to machine language. So again, we are basing this is a very theoretic analysis. We're basing this on the structure of the algorithm itself rather than the particulars of the implementation or the operating system. But you can see how quickly n cubed grows in comparison to n squared, n log n root n, log base 2 of n, or just a constant n. So, and obviously this advantage grows larger the larger n is. So, oh my goodness. Just because of time, I'm going to skip these questions. I don't really consider them to be very useful questions anyway. Essentially, the idea is, if this algorithm takes this amount of time for this n, how much would it take for that n? But we have a few slides like that I'm just going to skip in the interest of time. Sorry about that, guys, but, that's it. Anyway, the idea is here, the big takeaway here is big O notation. This is big O notation, even though you don't see big O anywhere on this slide. So, let's see if we can wrap up being careful with floating point before the end of class, and maybe I'll come back to those slides. So all the operations in the deepest for loop, we treat it as one operation. Thus, for two loops, it's n squared. Yes, good. Yes. Good. All right. Be careful with floating point. So, quadratic equation. We're bringing out all the old favorites. This is like the greatest hits for like late grade school, early high school math. So, quadratic equation solution. The quadratic equation, of course, is negative b plus or minus the square root of b squared minus 4ac over 2a. So, let's define ourselves a quadratic equation in Python. If we print the quadratic solution of something simple, like, say, 1, 0, negative 4, which is equation solution, which is actually the same function that we used the Newton's method on. Math is not defined. Well, I guess I'll just have to import it then. There we go. You can see that the roots of x squared minus 4 are 2 and negative 2, respectively. Sure, you know, not bad. Here's a question. What happens if you have something very large in the middle? Let's say negative 2 to the e, negative 2 times 10 to the 8th, which is a large number. We get these two numbers, which is interesting because well, that's interesting. It's not actually matching up what the slides say. There we go. That's better. You have to take one more. You have to push it one more. So the thing that I'm trying to demonstrate here is that this is b, right, in this equation. At this point, we have a multiplication of b against itself. We take b squared. Because this is so large already, if you were to take, if you print negative 2e9 and multiply it against itself, what you end up with is 4e plus 18. Now, plus 18 is big enough to absorb small values. You remember that absorbing of small values phenomenon that we were discussing earlier, right? There you go. We can even format this so that we see all of the decimal places. Am I getting the format wrong? Oh. There we go. So you can see, despite the fact that we're adding 10 here, that 10 is getting slorped right into the big number, this big number, and is not being represented at all because of the limitations of floating point representation. So that means that this algorithm isn't exactly stable. There are a couple of ways that you might be able to get around that, one of which would be using the decimal library instead of floating point arithmetic. But as you can see, this is demonstrated here. We have a loss of significant digits. So that's why we get the wrong solution. And, generally speaking, it's not good to use the wrong solution. So we can either use the decimal library for more exact precision at the penalty of slower runtime, or we can use an alternative formula that is more numerically stable and doesn't lead to large intermediate values. So there is Vieta's formula. So x1 times x2 is equal to c over a. Given the solution with larger absolute value, the smaller can be computed using Vieta, avoiding the loss of significant digits. So d is calculated as being the square root of b times b minus 4ac. That's this guy according to the previous. X1 is quadratic formula in the regular sense, and then x2 is calculated from the other one. So there you go. But yeah, so again, that's just one more thing to keep in mind with floating point numbers, is you always want to try to keep well away from the limits of the limitations of the floating point representation. And it can pop up unexpectedly because of the intermediate values that are calculated during program execution. And there we go. We have finished topic 6. I apologize for it being a little bit rushed, but, we did finish topic 6 this week, which is good. So anyway, good. If anybody has any questions, please provide those now. Otherwise, we're gonna sign off here. Thank you very much, folks. Ta-da! Do the extra marks from test 1 transfer to test 2 and 3? Yes, they do. Yes, they do. We didn't receive any feedback for assignment 3 yet. Send me an email about that. I'll look into it. Thank Yoi. Yoi, welcome. Alright, cool. There don't seem to be any questions, so I'll be seeing you. Keep in mind, if you wish to take advantage of it, I'm going to be having office hours for this class tomorrow at 1:30 in the Teams thing, so there you go. Take her easy, folks. Don't do anything I wouldn't do. Study up for the test,